Hey there, my name is Daniel from Marquette University, and I'm the captain for the Marquette Aeronautics and Robotics Systems team, MARS for short. This is our team's proof of life video for the 2023 NASA Lunabotics competition. Here, the robot has started a simulated NASA Lunabotics competition run from a random starting location and orientation. The footage you see here was recorded in the Discovery and Learning Lab and Engineering Hall here on Marquette's campus in Milwaukee, Wisconsin. Our preferred testing locations would have been Bradford Beach on the shores of Lake Michigan. On the screen now is some testing footage from one of the very rare days in early March, where the ground there was uncovered by snow and mostly dry. As you can see, the locomotion system can traverse a soft, sandy surface with ease. Even though it looks like a sunny beach in Florida, the temperature outside during that test was about 29 degrees Fahrenheit, which caused some issues with the steel shafts in our locomotion motors. The shafts underwent a ductile to brittle transition and failed under much lower stress conditions than expected. That week, our team repaired the motors and prepared for another run, but 2 days later, the beach looked like this. Although we replaced the motor and determined operating conditions that would prevent the motor shafts from failing in the cold conditions, the robot was not waterproofed and the auger would not have been able to break through the ice in and on top of the sand. Every day since the beginning of March, Bradford Beach and every patch of sand we could find has either been pits of mud or covered in snow and ice, so our team was forced to change the venue of our testing location to the indoor location here in Engineering Hall at Marquette's campus. Since the auger probably wouldn't have been able to mine through the concrete floor, we moved upstairs to the home of the Mars team, the Dynamics and Controls Laboratory, to simulate the mining system. For safety reasons, the robot was secured to the table, the locomotion motors were deactivated, and we maintained a minimum of 5 feet to the robot before filming. Also, to avoid repeatedly dumping sand into the lab, the dump bed was replaced with a bucket that did not actively sieve out the sand, and instead the sand was sieved afterwards. Before each test of the mining system, the sand and simulated regolith were prepared to ensure that the layer of regolith was 30 centimeters below the surface of the table, as specified in the Lunabotics guidebook. The biggest advantages of the auger mining operational concept are dust-tolerant design and dust-free operation. This is because all the simulated lunar dust being lifted is contained within the auger, so very little dust would be kicked away from the robot with an upward trajectory, minimizing the distance away from the robot the dust would travel. Meanwhile, the biggest disadvantage of the auger mining concept is the maximum overall mass flow rate of the mining system. Once the depth is maxed out, the robot will need to completely raise the auger, reposition, and dig through the dust layer again. This disadvantage is especially punishing in Lunabotics due to the short duration of the competition. But our team believes that in a real lunar mission, the advantages of the auger concept would outweigh the disadvantages. The Mars Senior Design team consists of 8 engineers in the Opus College of Engineering. I am Daniel Whalen, a mechanical engineer and team captain and lead systems engineer. There are 3 other mechanical engineers on the team. Marty Walls, the team scribe and lead testing engineer. Diego Chacon is responsible for the mining system and outreach coordinator, and Callan Schmeiser worked on the locomotion and dumping systems. The first electrical engineer on our team, Alex Mencia, worked on the electrical integrity of the entire subsystem and took the lead on the redesign of the electronic system. The second electrical engineer, Brian Montiano, worked on the local positioning system. Finally, the team has 2 computer engineers. Sal Giel is the lead on the autonomous navigation system, and Ian Stark, who worked on program integration into the robot operating system, or ROS, and the mining automation. Since one of the Mars team's primary goals this year was to achieve complete autonomy, the mining system was fitted with sensors to give feedback to the controller. The system uses gyroscopes to identify the auger tilt angle, a time-of-flight sensor to determine the depth via distance between the two gearboxes, and a strain gauge in the dump bed to measure the mass of regolith collected already. The robot is also designed to identify when the auger is jammed by detecting current spikes in the auger motor when the RPM reaches 0. To remedy jams, the robot will stop lowering the auger and briefly spin the auger shaft in the opposite direction before continuing. To navigate autonomously, the team implemented an artificial potential field navigation algorithm to generate a path to the mining zone and back to the sieve. The algorithm creates a virtual field around the robot where the goal location is an attractive force and obstacles are repulsive forces. As the robot moves towards the goal, it constantly senses its environment and adjusts its path to avoid collisions with obstacles. The result is that the robot is pulled towards the goal location while being repelled from obstacles, resulting in a smooth and efficient navigational path. In order to implement artificial potential field navigation, the robot will need to know the relative location of the sieve, mining zone, and obstacles. To identify the location of the mining zone or sieve, there are 2 RF beacons on the sieve and 2 receivers on the robot. Since each receiver can measure the distance to each of the beacons, the robot is able to triangulate both the location and orientation of the robot. This data can then be used to create the attractive forces in the artificial potential fields. Likewise, the robot must be able to identify the relative locations of the 2 kinds of obstacles, boulders and craters. To identify craters, the robot is fitted with time-of-flight sensors that can detect a sharp change in surface height ahead of the robot. To identify boulders, a LiDAR sensor was fitted to the front of the robot such that it has a 200+ degree field of view. Using the inputs from these sensors, the algorithm will generate a path and drive to the desired position. In the process of filming this video, the auger experienced a critical failure in the weld between the auger tube and the upper gearbox. With the increased testing of the auger to implement autonomous mining in the last few weeks, this failure likely occurred due to the buildup of wear on the inside of the auger tube where it could not be easily inspected. Because the team only officially measured 1 run of the mining system before the failure, and the repairs cannot be completed in time due to the curing of the time of the chemical welds, the team is using footage of 1 unofficial mining run that Dr. Vogelweed, our advisor, was unable to verify because the regolith was mixed back into the sand. To account for this, the team is doubling the officially measured 1.775 kilograms of regolith. Therefore, 3.550 kilograms of regolith were added to the dump bed during the navigational run in the Discovery and Learning Lab. This year, the dumping system was redesigned to provide a wider field of view for the LiDAR sensor and ensure that the navigation system can function properly. As the robot has traveled back to the sieve, the dump bed has securely stored the collected regolith while letting the sand fall through the holes. This dump bed is fitted with strain gauges to measure the weight of the collected regolith, as well as a pair of vibrators to help agitate the simulated regolith and let the sand fall through easier. Once the robot has arrived at the sieve, it is designed to use 2 time-of-flight sensors to properly align with the sieve. Once in position, the dumping mechanism is powered by a single actuator to lift and deposit the regolith over the edge. Now, here are clips of Dr. Vogelweed confirming the weights of mined and deposited regolith, robot weight, and robot dimensions.
78. 1,778.
1,178 grams of collected regolith.
3,208 grams. 3208.
3208. Okay.
60.
60.
Height is 60 centimeters.
103 centimeters.
103 centimeters long.
59 centimeters.
Width is 59 centimeters.
Max height is 95 centimeters. 95 centimeters.
Extended height is 95 centimeters.
Robot weighs 66.4 kilograms. 66.4.
66.4.
I'd like to thank you for watching, and a special thanks to our advisor, Dr. Vogelweed, and our reviewers, Mr. Cash and Miss Steinhardt, for their support and expertise throughout this year. We wouldn't have been able to do this without them. We'd also like to give a special thanks to our sponsors, the Marquette University Opus College of Engineering, Komatsu, Wisconsin Space Grant Consortium, and Vitech.